Hello there, guys. Let's get back into lecture 2 so we can pick up sort of where we left off. So again, this is lecture 2. These are the slides that are up on D2L. I'm going to go ahead and move into this. We start by talking about the mass in grams of 2 cubic inches of gold. Density of gold is given as 19.3 grams per centimeter cubed, and 1 inch equals 2.54 centimeters. Yay, that's exciting, right? So what would I do with that information? Well, I'd write down that 2 inches cubed gold, density equals mass over volume, which I know, equals 19.3 centimeters cubed, and 1 inch equals 2.54 centimeters. Yay, that's exciting. So what am I going to do with that? Well, I know that I want to change this, and I want to make it look different than that. I want to know what the mass in grams is, correct? So if I want to know the mass in grams, then I need to do something with this. And since I want to know mass in grams, I should write that down. Okay, so I have 2 cubic inches of gold. 2 IN cubed. Remember, anything above the line is multiplied, anything below the line is divided. It's not a very pretty line, but okay, fine. All right, well, I know that 1 inch is 2.54 centimeters. Why did I choose that one? Because it contains an inch, and I want to get rid of the inches. So I'm going to cube this whole thing. If I do that, then I need to do the same to that number out in the front, right? So let me pull up my calculator and my whiteboard again. And with my calculator, I need to do 2.54 cubed. And that gets me this nice, huge number. Okay, awesome, but I'm going to need that. All right, so that's what that is cubed. Now, I also know that 19.3 centimeters cubed it's grams per centimeter cubed. Oh, hold on, let me check that. Give me a second. I apologize. Yep, it is grams per centimeter cubed, which is going to change where I need to put that. So I'm now going to erase what I had there. We'll go back to the writing tool, and instead of dividing by 19.3, I have to multiply by 19.3. Now, why am I telling you this? Because one, I make mistakes too, and that's not right either. And two, those units do make a difference. And that's why I include them in all of my calculations. Okay, so my inch cube will cancel with this inch now that it's been cubed. My centimeters cubed will cancel with this centimeters cubed. And I need to multiply that number that I got over here by 19.3. Okay? I get 316 and a bunch of stuff out there. Yippee skippy. That's awesome. I have this big number. How many sig figs am I supposed to have for this number? Well, I started with 2 and nothing else. So I get 1 sig fig for this. So I can either write this as 3 times 10 to the 2 or just 300. That's the sig figs that we'd get. All right, either way, it comes out as 1 sig fig. So, okay, clear? Hope it's clear. Let's go ahead and pull back up the PowerPoint so we can continue to the next question. electron configuration of argon in both the full form, the noble gas notation, and the drawing out of the orbitals and electrons. So argon, full form, noble gas, and drawing out of orbitals and electrons. All right, let's go back here. So leaving what I had before, I want to do argon, full form, noble gas, which I'm just going to do is Ng, and then orbitals and electrons. Okay. So argon, what number is argon? Argon is number 18 on the periodic table. I have a periodic table that I'm looking at here. So argon is 18. That means we typically have 18 electrons. Reading from the periodic table, I know that I'm going to go and fill 1s, 2, 2s, 2, 2p6. So 1s2 takes me through hydrogen and helium. 2s2 takes me through lithium and beryllium. 2p6 is boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, we're then in the third row, 3s2, because he has those. That's sodium and magnesium. And then 3p, 1 would be aluminum, 2 would be silicon, 3 would be phosphorus, 4 would be sulfur, 5 would be chlorine, and 6 is argon. So that's what I have for argon. Notice 18 electrons, 2, 4, 10, 12, 18. So that's my full form. If I want to talk about the noble gas notation, strangely enough, that's just Ar. Awesome. And if I want to talk about the orbitals and the electrons, then we're going to do this similar to how we did this before. So 1s, 2s, slightly higher in energy is 2p, and there's 3 of them, so all 3 of these are 2p. I would normally list those as 2p, x, y, and z. Because I'm running out of space, I'm going to move over slightly, but this should be above where the 2p is, so please understand that that's what we should be doing. This is going to be 3s, and then we're going to have the 3p's. And again, 3s and 3p should be above the 2p's. So 1s has 2 electrons, 2s has 2 electrons. Remember, 1 spin up, 1 spin down. We then have 2p with 1, 2, 3, 4, 5, 6. And yes, I did draw them that way because that's how they fill the orbitals. They don't pair unless they have to. Now, can I write it the other way since I know I'm going that it's going to be full? Of course I can. Absolutely I can. But I'm not going to do that. It's just not how I do things. 3s paired. We have 3p1, 3p2, 3p3, 3p4, 3p5, and 3p6. So that's the complete designation there. And one other thing that I want to mention to you guys, remind you that we are talking about diamagnetic or paramagnetic, and of course this one is not magnetic. Okay, so that's what we're going to talk about there. All right, cool on that one. Then let's see what we've got next. How many significant figures are there in the following numbers? Okay, 1, 2, 3, 4, 5, 6, 7, 8. Because all of those zeros between the 2 and the 5 are significant. So that is 8. Writing in the wrong place. 2, 0, 5, and then a whole bunch of zeros. There are only 3 there. So the 2, the 0, and the 5. 2.050000, all of those zeros. Now I need to count all those zeros. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. because all of those zeros are past the decimal point and therefore are considered significant. So that's how many I have for that. Now let me back up. Okay, we clear on that? Now consider a solid with a mass of 19.462 grams and dimensions of 3.14 centimeters by 1.462852 centimeters and 2.7262 centimeters. And I want to know what is the density of this material. So I'm just going to jot some of those numbers down on the side because I'm going to need them when we get over to the other thing. So 19.462 grams. I have one dimension of 3.14 centimeters and a second dimension of 1.46285 centimeters, and then a third dimension of 2.7262 centimeters. Okay, well, that's fun. And now I'm throwing things around, which is also exciting. And now I'm going to flip back to my whiteboard. I'm going to clear this so I can actually see what I'm doing. And I'm looking for a density. So density has units of what? Oh, I need my other tool. Density has units of grams per centimeter cubed in this case, okay? Mass per volume, volume being centimeter cubed. Okay, awesome. Now, I said that it had a mass of 19.462 grams. One of my centimeters is 3.14. That's one dimension. My second dimension is given as 1.462825. 62825. And my last one is 2.7262. And of course, my decimal point has gotten lost in my mess. And that is centimeters as well. Okay, awesome. So I have a whole bunch of numbers. Yippee skippy. Let me pull up my calculator again. 19.462 divided by 3.14. Divide that by 1.462825 and divide that by 2.7262. And I get a number. Yay, 1.555 is a bunch of stuff. Now, how many sig figs am I looking at? Well, the first number that I looked at over here, this is 1, 2, 3, 4, 5 sig figs. This one is 1, 2, 3. 1, 2, 3, 4, 5, 6, 7 sig figs. And this one is 1, 2, 3, 4, 5. Lowest number is 3 sig figs, and that's from this 3.14. So if I come over here and give myself an equal sign, and then 1.55 grams per centimeter cubed. Okay, messy, not the greatest. I wish I could do this on a whiteboard, but unfortunately I haven't been able to manage that to this point. We're having some issues with that on campus. So that's our practice. Hopefully that made a bit of sense. And let's see what else we got with this. Now I'm going to go ahead and go to the next slide. And we're going to talk about atomic particles. And we talked about this a little bit before. We talked about protons, neutrons, and electrons. Remember that protons are positive, neutrons have no charge because they're neutral, and electrons are negative. The mass of a proton is 1.0073 AMU, neutron is 1.0087 AMU, and the electron is way tiny. Now, the Orbitron Gallery of Atomic Orbitals. Woohoo! What the heck is this? This is showing you what these orbitals look like. So in this first level, for hydrogen and helium, all we have is a 1s orbital. Down here, the second row, we have two electrons that can go into this 2s orbital. And then we have a 2px, a 2py, and a 2pz. In level 3, we have an s, and then a 3px, a 3py, and a 3pz. 4s, 3d, and then 4p. Now, you heard that right. So we have one orbital in the in the first row. It's 1s. There's nothing else. In the second one, we have s and p. Now, in the third level, we have s, p, and d. But the thing is, it fills s, p, 4s, 3d, 4p. The energy levels go that way. And so that's the way it fills. And that's why this line right here does not exist in the periodic table. Okay, that does give us some ability to do some funky things, and we can talk about that later. You need to know that these s orbitals are spherical, and you need to know that these p orbitals look something like this. And then we can sort of kind of draw the d orbitals like this. You aren't expected to know which one is which. You should be able to identify if somebody shows you one of those things, which one it is, okay? So that's why you need to know that. We also need to know kind of what shape they are. Questions about any of that? Hope not. If you have questions, remember, mark the time code, give me some idea what I was talking about, send me your questions via email or in office hours, and I'll do what I can to answer them. All right, periodic table. So we were just talking about this, right? In the first row, we have S, which contains 2 electrons, 1 and 2. Now, why is helium all the way over here and not here? Because it acts like a noble gas. Since this level can only contain 2 electrons, when that second electron goes in, it's completely full and it acts like a noble gas. Okay, we'll get to what I'm talking about with that shortly. This is your 2s right here. This is your 2p right here. This is your 3s. Notice there's no 3d yet. And this is your 3p. Then we go 4s. This is the 3d. And this is the 4p. Okay, so your p blocks are always going to be your row number minus 1. So since this is row 4, this is 3d. Okay, now when we get down to 5, we have the s, the 4d, and the 5p. Now there is a 5d, okay, that does exist, or sorry, there is also in 4 an F, but we don't fill that until down here. So where it says the lanthanide series, these right here, this is the filling of the F orbitals, okay? And F is always the row number minus 2. So notice that this row number where this lanthanide series sits is 6. So since this is minus 2 for the F, this is 4F. This is 5F, and it occurs here, okay? So we know that our orbital filling can be seen on the periodic table. We have 2 electrons that fill the 1s, 2 electrons that fill the 2s, then 6 electrons that fill the 2p. So you can see the orbital filling within the table. Now you can memorize the little diagram that puts them in the right order, but the table's already in the right order, so you might as well learn it in terms of your periodic table because you're always going to have that. You won't always have that diagram and yes, you can memorize it and spit it out on the test and work with it from there, but you always have this periodic table, and so you can use that as a reference, okay? I'm going to teach you to put as many things as you can on this periodic table so that you don't have to remember them, okay? So when we talk about the periodic table, groups, columns containing elements with similar properties are called groups, okay? That's usually because they have the same number of valence electrons, but we'll talk about that in a minute. So this is a group. Notice that it says group 1. And each one of these has a number. This is 1, this is 2. Over here we have 3, 4, 5. And notice they go all the way up to 18. But they also have these archaic numbers, 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, and then we come down here and we've got some other stuff that comes down here. We don't talk about those as much in the archaic sense because we didn't deal with them then. So those are your groups. You will need to know some of the names of the groups, and we'll get to those in a couple of minutes. Periods are the rows of the periodic table. The number of the row determines the highest valence shell orbital that the element has. Okay, what do I mean by that? So again, rows are these guys, and the number of the row, this number right here, indicates the N. So it's the energy level that goes with this. Now, if this is right here is 3, right? Then I know I have 3 different types of things in it. So I have S, P, and D. All right. And so this is S, this is P, and this is D. You have 3 different types in that particular group. Okay. In the 4, you're also going to have 4 there. Now don't go beyond that, but that's what we're talking about in terms of what we have for those. Okay. Types of elements. We talk about metals, metalloids, and nonmetals. So let me show you where those exist. The majority of this table is metals, and that includes these right here. Everything on this side of the table up to this staircase, so where this is dark gray, all of the rest of this, everything over on this side, those are your metals. These are our metalloids. So they exist in this gray section and in this blue section right here. Those are all considered metalloids because they have properties of both metals and nonmetals. Our nonmetals are these things over here. So carbon, nitrogen, oxygen, phosphorus, sulfur, selenium, all of our halogens, and all of our noble gases. So those are our nonmetals. It's going to become important to you later. They may ask you which part of the table is which, or how do I know what this is? You know, they may ask you based on where it is it a metal, a non-metal, whatever. So that's where it exists on your table, okay? So you need to know a couple of those groups, 1A, 2A, 6A, 7A, and 8A. So the alkali metals, the alkaline earth metals, the chalcogens, the halogens, and the noble gases. So let's look at those. So these are our alkali metals. These are our alkaline earth metals. These are our chalcogens. These are our halogens. And these are the noble gases. Okay, so that's what we have. Noble gas, halogen, chalcogen. I always do them backwards. But those are the ones that you're expected to know. All right? Information that you can find on the periodic table. An atomic symbol. The atomic number, which is the number of protons that it has. Its atomic mass, okay, which is again weighted for all of these things that we have, but that is also on there. The groups, all right, they'll give you the number for the groups. Remember that you need to know the alkali metals, the alkaline earth metals, the chalcogens, halogens, and noble gases. The metals, which are on the left side of the table except for H, the nonmetals, which are on the right side of the table, including H, and the metalloids are along the stair step in the main group on the right side. So again, that's the metalloids are right in here, okay? And you should recognize a lot of those from their work in microchips. So silicon, germanium is one of the things that we talk about, aluminum. Sorry, I almost called it aluminium because my husband's English. So those are our metalloids, okay? Yahoo! That was a lot of stuff. Go. That's our periodic table so far. Anything else? Let's find out. So we talked about our quantum numbers. Now, N is our principal quantum number. It's the energy of the orbital, and it corresponds to that row number in the table, okay? These are only whole numbers, possible values 1 and up. Then we have something called L, which is the angular momentum. It tells you the shape of the orbital, okay? When we talk about those things, if our L value is 0, then it's an s orbital. If our L value is 1, it's a p orbital. If our L value is 2, it's a d. If it's L value is 3, then it's an F. If your L is 4, that's a G. And if your L is 5, that's an H. We very rarely talk about those things. These can be whole numbers from 1 up to n minus 1. So, sorry, from 0 up to n minus 1. So if we're talking about row 1, and we can only go to n minus 1, that means all we have is 0. If we're talking about row 2, I can have a 0 and a 1. Hence why we see what we see on the periodic table. ML is considered the magnetic quantum number. It gives the direction of the orbital in space. Now, this has possible values from negative L to L, including zeros. What does that mean? Well, remember we showed this slide back here, and I said that this was a P, this was an X, and this was a Y. sorry, that this is an X, Y, and Z. Well, those correspond to the X-axis, the Y-axis, and the Z-axis. So that gives us our angular momentum, which tells us the direction. Now, you don't have to understand where that works, but that's how that fits into that, okay? And then MS is our spin quantum number. It indicates the direction of the spin, either clockwise or counterclockwise, and it's either negative 1/2 or 1/2, okay? Why do I care about all of this? Because no two electrons can have the same set of quantum numbers, all right? So we have to know what we're talking about. Now, I like to think about this in terms of apartments. So this is the apartment building. This is the actual apartment. This is the room, and this is the bed in the room, okay? So it's specifications, and just like two people are most likely not going to share a room in an apartment or a bed in an apartment, although there are exceptions. This is what we talk about here. So we can have more than one person in an apartment. We can have more than one room in an apartment. Sorry, we can have more than one apartment in the building. We can have more than one room in an apartment. This is the apartment. More than one room in the apartment, and only one person per bed. Okay. All right. Atomic orbitals. Again, we talked about N, L, ML, number of orbitals, and the atomic orbital designations. So, again, this one is 3 for number of orbitals, 2px, 2py, 2pz. Okay? So, again, all of those things go back to what we've been talking about with all of those numbers. Okay? Types of orbitals, an S can contain 2 electrons. It is spherical. They go up in size as you go down the table. So they have to get bigger as the energy gets bigger. So those can contain 2 electrons. Your P contains 2 electrons, 6 total, 2 in each of the 3 orbitals. So 2 in here, 2 in here, 2 in here. So any given orbital has 2 electrons. Total for the D is 10 electrons, 2 in each of the 5 orbitals. So 2 here, 2 here, 2 here, 2 here, 2 here. F, there are 7 orbitals for that, which means a total of 14 electrons. Okay? All right. Now, orbital energies. And I started to draw, remember I drew this before because we talked about it last time. You have a 1s, a 2s, 2p, 3s, 3p, 4s, 4p, and now the 3d is here in between the 4s and the 4p, the 5s and the 4d. Energies of the orbitals are not always as we would expect, so you can see that here. This little diagram will tell you what order you filled them in. All right, so if you want to know that diagram, you can know it. But the other thing that you can do is just look at what's on the periodic table, because nature fills things from the lowest energy up, okay? It says, as you add further electrons in the same principal quantum number, the same n, then the orbitals in that shell are further shielded. So when you add to p, the s orbitals are shielded. That's why it's lower in energy, okay? Oh my lord, we talked about all these things. Well, yeah, so n equals 1, 2, 3, 4, 5, 6, 7. Notice this is considered my S block. This is my P block. This is my D block where my N is -1, and this is my F block where N is -2, okay? So that's, again, just trying to show you the same thing that we've already said is on that table. Any questions about any of that? Questions, comments, problems, anything? Hopefully not, and if there is, you know that you can contact me about whatever you have. Electron configurations. Now, electrons have spin. That means they either spin clockwise or counterclockwise, -1/2 or 1/2. We'll show this by drawing arrows for each electron, either up or down, depending on spin. The Pauli exclusion principle states that in one orbital, you can only have one electron with a positive spin and one with a negative spin. Okay, so we're not going to both spin the same direction. It doesn't happen that way. Hund's rule tells us that electrons will not pair, have the same spin, or share, be in the same orbital, unless they have to. Okay, so when we start drawing things like P's, we have, no, sorry, wrong one. I wanted to annotate. Where's my little annotate thing? Yeah. So when we have P's, we're not gonna. Again, this is PX, PY, and PZ. When we fill, you go one here, then one here, because I don't want to share unless I have to. And then I go one here. Then now I have to share. That's the only place I can go, but I can't have the same spin, so I have to go like this. Okay? This is what I was showing you before. And that's why this applies. Okay? So that's how we do that. Since the two electrons have different spins, then paired electrons are not attracted to a magnet. So this situation right here is diamagnetic. Those electrons that are unpaired lead to magnetism. So for instance, if we had this same px, py, pz, but I only have one electron, they're not paired, that's a paramagnetic. Okay, so it's going to have magnetism. The hydrogen atom is 1s1. There's one electron present in the 1s orbital. So that's how we designate it. It's a 1s orbital with one electron. There are no other electrons in that. Okay, awesome. And it doesn't want to listen to me. Oh, there we go. Let's see if I can get rid of my... We should let you use it like an actual eraser. I could just draw over things, but no, I can't do that. So there we go. All right, so now I'm going to stop with that. So again, we talk about electron configurations. We can talk about lithium. Lithium is element number 3, so we have 3 electrons that we need to deal with. Obviously, the first 2 are going to go in the 1s, not paired. So up, or sorry, paired, but not the same spin, up, and then one up, one down. And then our third electron is going to go in the 2s. Beryllium is 4. We have our 2s is filled. Boron is number 5. So we have 1s2, 2s2, 2p1. Carbon is 6. 1s2, 2s2, 2p2. Nitrogen, again, 1s2 here, 2s2 here, 2p3. Oxygen, 1s2, 2s2, 2p4. Fluorine, 1s2, 2s2, 2p5. And neon, 1s2, 2s2, 2p6. Okay, so that's how that works. We continue to fill them in the energies, the ordered energies as we've seen. Okay, And for every new electron, we just draw one more, okay? So I want you to practice. All right. Let's do the electron configurations of elements 1 through 12 now. Well, you just saw the ones for 3 through 10. So I'm going to show you 1, 2, 11, and 12. And if we talk about 1, this is the 1s orbital, has 1 electron. So that's number 1. Number 2, again, we have the 1s orbital. I have 2 electrons, so 1 up, 1 down. So that's 2. We're going to do 11 over here, and then we're going to do 12 down here. So 11 is our sodium. Not well drawn boxes, actually. Give me a second, I'm going to erase the top. I'm going to draw them as just the lines. So 1s, 2s, 2p, all the way over, and then 3s. And again, writing them all on the same quote unquote energy in a line, they should all be together, but I didn't manage that. So 1s, 2, 2s, 2, 2p, 6, and then 3s, 1. So let's see if we can draw this one a little better. 1s, 2s, 2p, x, y, and z, and then 3s. And again, it's 1s, 2, sorry, forgot to draw the whole thing. I hate it when I do that. So 2s, 2, 1s2, 2s2, 2p, 6, and then 3s2. Okay, that's number 12. All right, so that's your practice for those. Any questions, comments, problems about all of that lovely stuff? And again, if you have questions about it, please let me know. I will do the best I can to answer your question. And if it's just that you can't read my handwriting or that I've written things in a crazy way, I apologize. I know my handwriting and my writing in crazy ways is neurotic. So, but I gotta work with what I got. Really wish I had a whiteboard. But it's too awkward to get the whiteboard to show as we're doing things right now. Going forward, I hope to be able to use one of the classrooms on campus to do this on a whiteboard so that it looks a little better. My handwriting is still not great on a whiteboard, but at least it's better than what you have here. Takes forever to erase. All right. Turn off our annotation. And of course, that was questions, so I already asked for those. There you go. Now, a condensed electron configuration, the noble gas notation, uses the noble gas closest to the element going over the element's atomic number. We put the noble gas in brackets and start the electron configuration with the noble gas left off. Okay, awesome. What the hell does that mean? Well, if we talk about calcium, right? Calcium is in that fourth row, and it's number, I can read this, 20. So the nearest noble gas, the one before that, is argon. So we see we have the argon in parentheses, and then we have 4s2. So nothing in the 3Ds, 4s2. Scandium, we have that argon 3D1, 4s2. Because after we fill the 4s, then we fill the 3D. All right. You can go down and look at the rest of the ones that have the 4s1, 4s groups and the 3D groups. The two that I want to point out to you are the ones with the asterisks, chromium and copper. Why are they noted like that? They look different, don't they? There's only one electron in the s orbital for both of these. Why on earth is that true? When we get to this point, we would have a situation where if this was completely full, then we would have 1 over here, 4 over here, right? And okay, but it actually is lower in energy to have 1 in the s, it not paired, and then the d half full, than it would be to have the 4s filled and 3d not half filled. Okay, similar situation when we get down here and talk about copper. So again, we're going to take one of these s orbitals and move it to the d orbital, because now the d orbitals are completely filled, and it's lower in energy for us to have 1 electron in the s orbital and either have the d orbital half full or completely full. All right, so you need to remember those 2 exceptions, because they're the weird ones, and of course we like to ask about the weird ones because we want to see if you know what you're talking about. All right, these are just some of the other ones so that you can see what they look like up until things, and we run into the same situation with these that we did with the other ones. We have a couple of exceptions. So this 5d1 6x2, and this is so that we can get a half full f orbital. All right, so the same exceptions exist in the f's as well. All right, so we're talking about the exact same thing that we talked about before, having a lower energy if that f is half full or completely full, and taking one of the electrons out of the s to do that. Okay, or out of the previous d to do that. All right, effective nuclear charge. So as I go across a row in the table from left to right, what happens? Well, as I go from left to right, I'm adding both protons in the nucleus and an electron on the outside. Now, the nucleus is very small, and the electrons are all over the place around that. So the positive charge in the center gets larger, but the negative charge isn't really felt there. The same number of electrons are on the inner shells, right? So the effective nuclear charge gets bigger. It looks bigger because we're still talking about the same number of electrons that are surrounding it for the most part. Remember that as we get really far out, they're very not together, and so it doesn't really see it the same way. Now the increase is only slight, but it does go up as you go down a column. The effect vertically is much smaller than horizontal. So effective nuclear charge goes up as we go from left to right, and it goes up as we go from top to bottom. Okay? We can talk about the atomic radius. All right? Now, for reasons that seem really interesting, who's bigger, row 1 or row 5? Yes, we do get bigger as we go down the table. Awesome. But we get bigger as we go right. Why is that? Because the effective nuclear charge is higher. If the nuclear charge appears bigger, then the electrons pull in more. Okay, so that's why we see that. We see the smallest ones over on the right, and the biggest ones over on the left. Now, my atomic radii increases as I go down a column, and increases from right to left. Okay. Our ionic radius is going to have some weirdness to it as well. For the same charge, the trend is the same as the bonding radii. An isoelectric series is one that has the same charge on all items in the group. As nuclear charge increases, the radii decreases. So the bigger the nuclear charge, the smaller the radius. Okay. More highly charged ions are smaller than ones with lower charge, even though there are more protons. Okay. So even though that nucleus has gotten bigger, that electron shell pulls in more for the same reason that we just talked about with the ions. Okay. Ionization energy. How much energy is required to be given to an atom to remove an electron? So if I want to go from fluorine to F minus, that's how much energy is required to do that. Ionization energies increase as you continue to remove electrons. So the second ionization energy is always higher than the first. There is a very large increase in ionization energy when you remove from an inner shell electron. So if we're talking about something that's in that second row, if we're talking about lithium, say, I can give up one electron very easily to become Li+. But if I want to become Li2+, I'm then taking from that first row's electrons, which are the inside ones, and that's much, much harder to do. So ionization generally increases as you move from left to right in a period, so across the table, and generally decreases as you move down a column. Okay. Electron affinity, the energy change that happens when an electron is added to an atom. So for nonmetals, this is the energy given up. For metals, it's the energy required to add to it. Note that the energy being released is negative. Positive energies are energies required to add. So if the energy released is negative, that's spontaneous. It doesn't require energy to do it. Okay, it gives up energy in doing it. The most favorable is adding to F minus. Higher up and more right is the most favorable, and therefore the most negative values. So it increases as you go down and left. It's less negative, less favorable, and therefore increases as you go down and left. Yay! Can we summarize all that crap? Yes, absolutely we can. Now, this is not in the ones that I posted, but I can give it to you if you guys are looking for it. So ionization energy goes up as we go over and up. Electronegativity, which we'll talk about later, is the same thing. It gets bigger as you go over and up. Atomic radius gets bigger as you go down and to the left. Electron affinity is, this is the negative portion of it. So as I go up and over, it's more favorable. All right. Metallic character is higher in this corner down here with the metals, and the non-metallic character is higher over here where the non-metals exist. Okay? So those are our periodic trends. You will need to know those trends because you'll get asked about them. All right. Molecules and molecular compounds. What are molecular substances? They're made from non-metals bonded to other non-metals. So that's a molecule. These can be the same element as in O2, okay, that's a molecule, or different as in CO, which is a compound, and it's called a molecular compound. Use of atomic symbols and subscripts to convey the proportions of a compound. What the hell does that mean? Well, H2 is 2 hydrogens. So hydrogen is the atomic symbol. The subscript determines how many of them you have. H2 is diatomic. It contains 2 atoms. H2O is polyatomic. It's a molecular compound also, and it contains more than 2 atoms. So anything that's more than 2 is polyatomic. Anything that's 2 only is diatomic. And again, anything that's the same is considered a molecule, and anything that is different is considered a compound. All right? Molecular formulas are those that represent exactly how much of each atom there are in a formula. For instance, hydrogen peroxide, H2O2, is a molecular formula. 2 hydrogens, 2 oxygens in this. But we also can talk about empirical formulas, and they're different than molecular formulas. Empirical formulas are the smallest whole number ratio of the atoms in the formula. For instance, for hydrogen peroxide, HO is the empirical formula because you can divide 2 out of both of those numbers. So that's the lowest whole number ratio of those atoms, and therefore is the empirical formula for the molecular formula H2O2. Okay? Now, we need molecular models. Why? Because we can't really see a single molecule, but we can talk about them in many, many different ways. So our molecular formula is given by H2 for hydrogen, H2O for water, NH3 for ammonia, and CH4 for methane. We can draw a structural formula that explicitly shows both of those molecules and the bond between them. Okay, same thing for water, ammonia, and methane. We can have a ball and stick model, which is just a space-filling way to look at that structural formula. It gives you a better idea what these things look like in three-dimensional space, okay? And so this is the format that we'll be talking about the most this term. We can also do a space-filling model. So because the electrons exist in this big nebulous cloud around all of these atoms that we do this, we can talk about a space-filling model that'll tell you where the highest probability of finding those electrons are, and that's what these are, okay? These are just the same thing as these. There is no difference. You can tell that there are two different things in this, because one is red and these are gray, so they're different. These two are the same because they're both gray. So differences in color are significant for those, all right? Empirical formulas. How do we find them? So we talked about them. We know it's the smallest whole number ratio that we can have for something. It's determined by experiment. It's the smallest whole number ratio of atoms in the molecule. So again, hydrogen peroxide H2O2 is a molecular formula describing all atoms in the molecule. This is a true formula. HO is the empirical formula we determined for hydrogen peroxide. We know how to determine the empirical formula from a molecular formula. We'll figure out how to do it in the other direction a little bit later. So determine the empirical formulas for the following molecules. C6H6. Okay, C6H6. I can divide both of those by 6, and so I get CH as my empirical formula. N2O5. 5 is not divisible by 2, so I'm stuck with N2O5. C4Cl4. Shocking. I can divide both of those by 4, so I get CCl. PCl5. No way I can reduce that. So that's still PCl5. In this case, the empirical formula is the same as the molecular formula. C6H12O6. Well, all of those are divisible by 6, so my empirical formula is CH2O. So if I divide everything by 6, that's what I'm left with, okay? So what is the relationship of the molecular formula to an empirical formula for each of these? i.e., what number do we have to use to multiply to get to the molecular formula? Well, here it's 6, all right? So if we're talking about this particular one, we're talking about 6. This one is 1. This one is 4. This one is 1. And this one is 6. Okay? So it's just whatever number that we have. It's a relationship between the molecular formula and the empirical. Okay? And see, this is when we should have erased everything, but we didn't. Really upsets me that I can't do that. I had high hopes, high apple pie in the sky hopes, that I'd be able to go to the next slide and it would be gone, but I knew it wasn't going to happen, so why did I do it? Anyway. All right, in this particular slide, we want to know what's the empirical formula and what's the ratio, what's that number that we need to multiply by to get to it. So C6H12O6, our empirical formula was CH2O6. 2O, and we multiply that by 6 to get there. Or CHO, if that's our empirical formula, then and we multiply by 3 to get our molecular formula. That's C3H3O3. And I'm not going to draw the rest of them. B5H7, if I multiply that by 2 to get the molecular formula, that'll give me a molecular formula of B10H14. If my molecular formula is C4H2O2, then my empirical formula is going to be C2HO. And I have divided this by 2 to get that, okay? If my empirical formula is CH2 and I have to multiply by 2, my molecular formula is C2H4. If I have C4O2 as my molecular formula, my empirical formula is going to be C2O. And that's going to be a 2 for the ratio as well. Okay? Awesome. Yay. I like it much better when this is projected onto a whiteboard and I can just draw these and then erase them, but that's not what we're doing. Okay, so questions, comments, problems on that? I hope not. But again, if you do have them, let me know. Valence electrons. So let's again consider carbon. Now, carbon is number 6, so there are 6 electrons because we have 6 protons and it's neutral. So 6. Are they all in the same physical space? No, absolutely not. Carbon, which is number 6, is in the second row, and we know that those, so we have 1s2, 2s2, 2p2. So we know that they're not all in the same place. It's in the second row of the table, and implies that there are 2 energy levels at 2 different distances from the nucleus. We know that now that there are only 2 electrons in each s orbital. Awesome. So we know that C has 2 E minus and 1 s, 2 E minus and 2 s, and 2 left over. How many electrons are there in the outer shell? Well, the outer shell, the N number for that is 2. So the outer shell contains a total of 4 electrons. 2 in the s orbital, 2 in the p orbitals. Are they all available in the same way? Well, no, actually they're not. So we have 2 of them in the s orbital that are paired, and I have 2 in the p orbitals. I may not really know what that means yet, but I do know that the p is slightly higher in energy than the s is, so there's going to be something there, and we'll get to the rest of it. The electrons in the highest energy level, the highest quantum number, and the highest angular momentum are called valence electrons. Those are the electrons that we can work with for bonding in molecules and for making positive ions, called cations. This is also where additional electrons are added to make anions. So if we want to make a negative ion, we're going to add electrons to that same shell. Okay, so that same quantum number. I talked about adding electrons to make ions. So what's an ion? A charged particle. Consider Na. Remember how we discussed it wanted to become a noble gas? Well, Na is number 11. It's in the 1A group. So if it loses 1 electron, it becomes like neon. Okay, awesome. So we take 1 valence electron from the outer shell and give it to something else. Something. We don't care what, just something. In that case, it has a positive charge, and Na plus is an ion. It's a charged particle. Ionic compounds are formed between metals and nonmetals when the atoms have become ions. So ionic compounds between metals, stuff on the left side of the table, and nonmetals, stuff on the right side of the table. They mix in fixed ratios based on their charges. Now, positive ions are cations, negative ions are anions. So we know that metals want to be cations, they want to lose electrons, and nonmetals want to gain them to be anions. But how many will they lose or gain? That depends, for the most part, on where they live in the periodic table. So let's guess our way through a few. So let's talk about lithium. Again, lithium is element number 3. It's in group 1A. So if it's in 1A, it can lose 1 electron to become like helium. So that's going to be Li+. Oxygen is number 8. It's in the second row and in this P group. And it wants to be an anion because it's a nonmetal. So in order to get to the nearest noble gas, it needs to gain 2 electrons to be like neon. So O2 minus. Ca is in group 2A. So it's an alkaline earth metal. It wants to be a cation because it's a metal. And it's going to lose electrons to go back and be like argon. Okay, great. It has to lose 2 electrons to do that. Awesome. Cl is number 17. It's a nonmetal, so it's going to want to gain an electron to become negative. The nearest noble gas is argon, so it's going to gain 1 electron to become like argon. Awesome. We can do that. So based on where they are in the periodic table, we should be able to guess what their charges are. Doesn't always work that way, but it does for most things. So again, we can talk about sulfur. Sulfur is under oxygen. Oxygen picked up 2 electrons to become like neon. Sulfur can pick up 2 electrons to become like argon. Since it's a nonmetal, it's going to pick up electrons to be negative and to be an anion. Sr is down here. It's number 38. It's in group 2A, so it's a metal. It wants to lose electrons to be like the nearest noble gas. The nearest noble gas is krypton. In order to do that, it has to lose 2 electrons because it's in group 2A. So Sr2 plus. K is number 19. It's in group 1A. It needs to lose 1 electron to become like argon. So it's going to be K plus. F is number 9. It's right next to neon. So since it's a nonmetal, it wants to gain an electron to become like neon. Ca is in group 2A. It wants to lose electrons since it's a metal to become a cation, and it needs to lose 2 electrons to become like argon. Nitrogen is a nonmetal, so it's going to have a negative charge, and it needs to pick up 3 electrons to be like neon. Okay, since it's number 7, it needs to pick up 3 electrons to be like neon, which is number 10. I, on the other hand, is number 53. It's one of the halogens. It's in group 7A. And so it needs to pick up 1 electron to become like Xe, or xenon. All right, so I minus. Ba. Well, Ba is in group 2A again. It's number 56. Since it's in 2A, it needs to lose 2 electrons to go back and be like xenon. So Ba2 plus. Cs. Cs is cesium. It's a metal. Its number is 55. It's going to lose 1 electron to go back and be like xenon again. Okay, so Cs plus. And Se, well, first we got to find Se. Se is a nonmetal. It's number 34. Since it's a nonmetal, it's going to want to pick up electrons to become negative. And in order to get to the nearest noble gas configuration, it needs to pick up 2 electrons to have that full octet. Okay, so it's going to be Se2 minus. Questions, comments, problems about any of that? Awesome. Now notice that the only ones we've done so far are in the S groups and the P groups, because those are the easy ones. And we talked about this. So in group 1A, we're going to be +1, 2A +2, 3A, we can be +3, all right? But some of them have exceptions and can also be +1. We don't necessarily know what these ones in the middle here are going to be, so we don't talk about them all too much. They are metals, so or these 2 are metals, so they're going to pick up electrons. This one is a metal, so it's going to pick up electrons. Boron, carbon, these metalloids typically don't form ions. They just form bonds with other nonmetals. Nitrogen is a 3-. O is a 2-. S is a 2-. Se is a 2-. Te is a 2-. And these 7A halogens pick up 1 electron. So it can become an H-. We can also become an H+. F-, Cl-, Br-, and I-. Okay? Common polyatomic ions. What's a polyatomic ion again? Oh, wait. It has more than 1 atom. So poly means more than 1. All right. We did say that polyatomic typically means 3. But sometimes what we're looking at in here are 2, and these are still called polyatomic ions. So mercury 1, also called mercurous, is Hg2 2+. Now, it's mercury 1, so if we're talking about the charge on each of those mercuries, it's 1+. All right? Ammonium is NH4. We have anions, peroxide, hydroxide, cyanide, phosphate, monohydrogen phosphate, dihydrogen phosphate, carbonate, hydrogen carbonate, which is also known as bicarbonate. Why are all of these here? Because you need to know them. You need to be familiar with them. And if they ask you to write a formula with one of these, you should be able to do it. Okay. That means you need to know what the formula is going to look like, as well as the charge. Okay. So this is something that you should be trying to memorize. Some of the other ones that we often talk about, acetate, we talk about acetic acid and acetate. Oxalate, chromate is a big one. So chromic, dichromate is C, so 2 chromiums, dichromate. Permanganate, nitrate. So if we add an H to this is a nitric acid. Nitrite, so we can add an H and it'd be nitrous acid. Hypochlorite is ClO minus. Chlorite, chlorate, and perchlorate. These are going to be important when we get to the acids, okay? But they're all Cl and some number of O's with the same charge, okay? Questions, comments, problems about the ions we have. All right, so where are we going now? What are the charges of the D and F block metals? Now notice we hadn't talked about these. Realistically, it could be a lot of things. The most common is 2+, resulting from the loss of both s electrons. I don't always know what the charge on these are, and they can have more than one charge. So like iron can be 2+ and 3+. So you'll usually have to be told what the charge is, either by seeing the charge on the metal, so Fe3+ would be a 3+, obviously, the name of the compound, which will tell you, like iron 3 would be written as iron parentheses Roman numeral 3, or from inspection. So if we had iron 3+ and it made a compound with oxygen, it's going to be Fe2O3. And because we cross multiply, the charge on the Fe has to be 3. Okay, and we'll talk about that again in a few minutes, but that's what we mean by from inspection. So charge on the metal. So like I said, it's directly on the metals. We can see 2+, 3+, 2++. Name of the material, iron 3 oxide, zinc 1 chloride. Sometimes this is just written as zinc chloride. If nothing's indicated here, we know it's 1. Copper 2 oxide. Okay, so we know that this is copper 2, so that's what we have. Inspection, Fe2O3. Since we know that the charge on oxygen is -2, from what we saw in the periodic table, then if this charge is 2-, and we need to have as many pluses as we have minuses, then we need to have 2 Fe's. And to make that work, this 3+ has to be multiplied by 2. And this 2- has to be multiplied by 3 to give us a total of 6. 6+ and 6-. Now, Cl is -1, so this Zn is +1. O is -2, so this Cu is 2, Cu2. So copper 2 oxide is this right here. And Cr, in this case, since oxygen is 2-, we have 4 of them, so that's a total of 8-. But we want one of those minuses left, so we need Cr to be +7 to make that work. Okay, in that particular case, that's what it is. All right? Questions on that? Do we want to talk about electron configurations again? Oh, of course we do, because there's a slide on it. So for atoms, that's easy. We just follow the table, like we talked about before. What happens if I have an ion? Well, we always take the electron from the outermost shell. So if we're talking about this particular ion, 1s2, 2s2, 3d10, 4p, 4p6 is krypton. So that's a fold for krypton. All right, if we're going to make an ion out of that, we take it from the outermost shell in the above, that's the 4p. So we're going to take the electron from there if we're going to do it. Same trend will be true when we add electrons. If we're going to add electrons to this, it will get put into that 4p, right? If there's no space in the 4p, we'd put it into the 5s, okay? And in this case, there is no space in the 4p, so we'd have to add it to the 5s. There are a few weird exceptions that have to do with the exceptions we saw in the electron configurations from last time. So again, if it gives us a situation where we can have a half empty or completely full D, F, G, whatever, that's going to be an exception that we will do. All right? So that's how we'll work that. Organic materials. Oh, Lord. Most of the stuff so far we've talked about it has been inorganic. That means it doesn't contain carbon. That's the only thing we care about. And you may hear me if somebody's talking about, oh, I have organic strawberries. And I'm going, I hate those inorganic strawberries. Because by definition, since strawberries contain carbon, they have to be organic. And I know that's not what they mean by that term, but it really irritates the heck out of me. Hydrocarbons contain only hydrogen and carbon. Alkanes are linear chains of hydrocarbons. And when one or more hydrogens are replaced on an alkane, they are replaced by functional groups. These groups determine many of the properties of the molecule. Formulas can be written in two ways. Okay. All right. So that was our organic stuff. That's all we're going to talk about in terms of organic. You need to know that it's made from nonmetals. You need to know that it contains carbon. Carbon, hydrogen things are hydrocarbons, and alkanes are linear chains of hydrocarbons. And we can write these in many, many, many different ways. Often we write them in strange ways so that we understand if it's an acid or a base. And we'll talk about that when we get to that portion of it. So ionic compounds. So now I know that Ca becomes Ca2 plus and Cl becomes Cl minus. Yippee skippy. Now if I have Ca2 plus and Cl minus hanging around together, do they stay by themselves? No, they don't like to be separated. So they're going to hang out with each other. All right. When that happens, how do they come together? Do I get a Ca and a Cl? Do I get two Cas and a Cl? Or do I get a Ca and two Cls? What do you think? Oh, yeah, that makes sense. It would make sense that it's CaCl2. Why does that make sense? Because Ca is 2 plus. So I need two Cl minuses to do that. Okay, so it's cross multiplication. All right. So since this is 2 plus, we need 2 here. Since this is 1 minus, we need 1 there. All right. It's net neutral. That's the way we do it. Awesome. Now, if I want to name an ionic compound, I name the cation and followed by the name of the anion. But on the anion, we change it from chlorine to chloride, oxygen to oxide. We have to indicate the number of cation, indicate the charge of the cation in parentheses and Roman numerals if required. So if more than one of them can exist, we absolutely have to do this. We can always do it. It's never wrong to do it, but you don't have to do it if there's only one thing you can get. So like K doesn't need to be written as K Roman numeral 1, because it's always K plus. Now common names can be used, but I don't recommend them. We saw one of those before, Mercurus, for that Hg 2 plus. You want to know what they mean if you run into them, okay? So you should be able to say in like a matching case, which one of these is Mercurus, that kind of thing. All right, there are common names that we will know for some things. Water, ammonia, some things like that are very common, and so hence they're common names. Now let's practice naming ionic compounds. So Rb2O. So Rb is rubidium, and that's rubidium oxide. Because again, rubidium is one of these ones. All right, hold on. That's in group 1. All right. So it loses 1 electron to become Rb plus. And since oxygen is -2, then we have to have 2 of them. So this is rubidium oxide. Now, calcium is Ca. We know that's in group 2A, so it becomes Ca2 plus. And bromine, so it's calcium bromide. And there are 2 calciums because of that charge. MgS. Now, what is Mg? Mg is magnesium. S is sulfur, but again, we call it sulfide, so magnesium sulfide. Na3PO4. Well, PO4 is a polyatomic ion. It has a 3- charge on it. This is called phosphate. And Na is sodium, so this is sodium phosphate. Zn is zinc. It is one of the ones that becomes a 2+. All right. So this is called zinc oxide. All right. Now, again, we don't normally need to say what they're going to be if we know what their charge typically is. All right. And Zn we know is going to be a 2+. Now, what is the formula for the foam? Tellurium 4 chloride. Well, it's Te for tellurium. We know its charge is 4+. Chloride. So I need TeCl4. All right. Manganese 2 phosphate. Manganese is Mn. I know that the charge on that is 2+. The phosphate is PO4 3-. And so Mn, this is 2+. And then PO4 3-. And so I need to have Mn 3 and PO4 2. Okay, cross multiplication. So I need 2 of these -3- groups to make a total of 6-. And I need 3 of these guys to make a total of +6. Okay, so that's how that particular one works. Zinc 1 nitrate is going to be Zn+. Nitrate is NO3-. So that's ZnNO3. Same charge, so we only have 1 each. Awesome sauce. Aluminum oxide. Well, aluminum is one of those ones that's along the stair step. We saw it before. Aluminum typically has a charge of 3+. And based on where it is above aluminum, below boron, that's what I meant, we know that it's going to lose 3 electrons to do that. All right. So it's going to be aluminum oxide. Since the aluminum is 3+, then we need to have, and the oxide is 2-, then we need to have Al2O3 to make the charge work. Okay. And calcium bromide. Calcium is a 2A group, so it's going to lose 2 electrons to become Ca2+. Bromine is a halogen, so it's going to lose 1 electron to become bromide, Br-. And so we have CaBr2. Okay? Questions, comments, problems about that? Naming molecular compounds. So we named the ionic ones. Now we got to name the molecular ones. Systematic names are those you need to know. Common names may be referenced. Some need to be known. Now, a systematic name says that we're going to talk about things with prefixes on them to tell us the number of them. So binary compounds are named by naming the atom that comes first in the formula, and then name the second item and change that to ide. So just like we did before. For example, let's name NO. N is nitrogen, O is oxygen, so this is nitrogen oxide. Okay, but we know that this can be NO or N2O. So how do we tell them apart if they're both nitrogen oxide? We can't. So we attach prefixes to the names to indicate how many there are. If an item is only one, we can call it mono. Okay, this is often omitted for the first element. So in this case, we have nitrogen monoxide. Okay, so 1 nitrogen, 1 oxygen, and 2O is dinitrogen monoxide. All right. That way we've indicated explicitly how many of those things we have. And those prefixes are given in a table. You need to know what they are. Non-metal to non-metal bonds can be configured in a number of combinations. To make sure that we are clear on which one it is, we usually use prefixes for each element to know how many there are. Dihydrogen monoxide is H2O, or water. Dinitrogen tetroxide is N2O4. Prefixes that you need to know are on the next slide. Dun dun! Mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. Now remember that we can eliminate the mono, all right, for the first element, but if it's on the second element, we need to include it, all right? Questions, comments, problems about that on that? And yes, this is a table from a different book, so the number doesn't make any sense. Naming molecular compounds again. Compounds containing hydrogen are often non-conforming to nomenclature rules. B2H6 is diborane. CH4 is methane. SiH4 is silane. NH3 is ammonia. PH3 is phosphine. H2O is water. And H2S is hydrogen sulfide. So why is this non-conforming? Because it should be dihydrogen monosulfide. So we know that there are some things that we don't do in that way. Note that even the order of writing the elements of the formulas for hydrogen compounds is irregular. Sometimes the hydrogen is second, sometimes it's first. All right. And that's usually done for a particular reason, but we'll talk about those reasons later. So these are some of the common things that you will need to know because they don't follow the normal rules. Now, if you were to name one of these, carbon tetrahydride, it's not technically wrong. And so you should be given credit for that. Okay, if you're not, it's because people are being dicks. But that's what happens. If you see something like that on a test and I haven't found it to say that you can do it either way, then let me know and we can talk about getting you points for that, okay? Naming simple compounds. So first thing I have to ask, what kind of compound is it? Is it ionic or is it covalent? All right, am I talking about charged particles or non-metal to non-metal? If it's ionic, it's composed of cations and anions. Covalent compounds are non-ionic, not composed of cations and anions. Typically, only nonmetals are present. Or, we'll get to this, there are acids. These are things that produce H+ in water. Typically, hydrogen is written first. Now, type 1, for the ionics, only one type of cation is observed, and so we have the rules that we had before. Type 2, there's more than one type of cation possible. All right. Type 3 is the covalent, non-ionic. And we talk about that with the systematic naming, right? This is the one where we don't have any numbers associated with it. This is the one where we have the Roman numerals associated with that particular metal, okay? So we'll consider the following cases. Ionic compounds, main group metal to non-metal polyatomic. Name the metal and then the non-metal. Transition metals to non-metal polyatomic. Name the metal followed by its charge in parentheses, then name the non-metal. Molecular compounds, non-metal to non-metal. Name the atoms in the order presented. Indicate the number of each present using the prefixes. Okay? Questions on that? Whew. This is some practice for you. I have indicated all of the answers in the notes that are down below this, but these are some things that we can talk about. I want you to try these on your own and then look at the answers that are given. All right? If you have any questions about it, please let me know. Questions, comments, problems. This is the acid part. Acids for now are identified as substances that give off H+ in water. In that case, formulas for acids contain one or more hydrogen atoms and an anion. Names are as follows. Hydrogen fluoride, HF. HF is hydrofluoronic acid. Corresponding anion is fluoride. HCl, hydrogen chloride. HCl is hydrochloric acid. The corresponding anion is anion is Cl minus. Now, I want you to know these. Why do I want you to know these? Because these are mostly strong acids, and so you'll need to know them anyway. Now, HF is an exception, but I want you to be able to know all of these things, all right? So, and this note down here tells you that we talk about when they're in aqueous solution, that's when we call them the acid names. If they're not in aqueous solution, we typically don't, all right? These are your reference acids. So according to your textbook, you should know all of these things. Carbonic, chloric, nitric, phosphoric, and sulfuric. These are polyatomic acids. And then you need to know the oxoanions. So phosphoric acid, dihydrogen phosphate, hydrogen phosphate, and phosphate. So what does that mean? We've taken the phosphoric acid, taken one of the protons off of it, and you need to know that that's dihydrogen phosphate. We take the second proton off of it, and it's hydrogen phosphate. We take the third proton off of it, and that's phosphate. Okay? This is a systematic way to look at what we just talked about. Now, personally, this didn't make a lot of sense to me. So I just memorized the names. It was easier for me to do it that way. But this is a way that you can look at how do we name these things based on the number of oxygens that are there, okay? All right. Naming bases. Woohoo! For now, bases are defined as compounds that yield OH minus in solution. So NaOH, KOH, BaOH2, so sodium hydroxide, potassium hydroxide, barium hydroxide. Ammonia, NH3, is also a base. Why does that happen? Because NH3 is the conjugate base of a weak acid. So it will pick up a proton from water. So NH3 plus H2O goes to OH minus plus NH4 plus. And so it still gives off this OH minus and therefore is defined as a base. Hydrates. Dun, dun, dun. These are compounds that have a specific number of water molecules associated with it. So barium chloride with two H2Os is barium chloride dihydrate. That's how we name that. Since those things are associated with it in its normal state, then it's dihydrate, hydrate, heptahydrate, tetrahydrate. So septa is the 7, tetra is the 4. When we drive the water off of this, if we choose to do that, we call it anhydrous because it has no water. Inorganic compounds. Here are the formulas, common names, and systematic names of some common compounds. You could be given either one on a test and asked what one of these names look like as a formula. So H2O is water, dihydrogen monoxide, NH3 is ammonia, trihydrogen nitride, CO2 is dry ice, solid carbon dioxide, NaCl is table salt, sodium chloride, N2O is laughing gas, dinitrogen monoxide, CaCO3 is marble, chalk, or limestone. It's calcium carbonate. CaO is quicklime, calcium oxide. CaOH2 is slaked lime, calcium hydroxide. NaHCO3 is baking soda, sodium hydrogen carbonate. Na2CO3.10H2O is washing soda, sodium carbonate decahydrate. MgSO4.7H2O is Epsom salt, magnesium sulfate heptahydrate. MgOH2 is milk of magnesia, magnesium hydroxide. And CaSO4.2H2O is gypsum, calcium sulfate dihydrate. Questions on that? That is everything for lecture 2. So that's everything for lecture 2. I hope that that is helpful for getting you through some of the stuff that wasn't just me reading the slides. So trying to show you what some of these things are. Now, if that wasn't helpful, please let me know and I will see what I can do. Again, my preference is to have you tell me which lecture it was, what I was talking about, and the approximate timestamp so that then I can go back and review what I was doing so I can see if I can explain it to you in a different way. All right. Thank you very much, guys. I appreciate you. I will go ahead and post this video as soon as it is done doing its thing and converting. And I will see you later. Thanks. Bye.